Today, we want to remind ourselves of the fundamental theorem of calculus, what it means and how we can interpret it. And then we'll remind ourselves of the relationship between the signs of the first and second derivatives and the direction of the function and the concavity of the function. Okay, so the fundamental theorem of calculus, we have a continuous function on a closed interval. Then the definite integral from a to b of f of x dx is the capital F at b minus capital F at a, where capital F is an antiderivative of f. That is, capital F prime is the function f. So when we're integrating, what this means to interpret this, when we integrate a rate of change over an interval, that tells us how much the function has changed on that interval. So we're integrating capital F prime, we're integrating a rate of change of a function. That will tell us how much the function has changed on the interval. That's how we can interpret the definite integral. The definite integral of the rate of change of a function over an interval gives the change in the function over the interval. So what this means is that if we integrate a velocity, that will give us a change in position, because velocity is the derivative of the position. Velocity is the rate of change of position. So if we integrate the velocity over between two times, that will tell us the change in position over that time. So for example, if we integrate from time a to b a velocity function with respect to time, that's going to be a change in position. From time A to time B. We read that at the change in position by evaluating the position at B where we ended up and evaluate the position at A where we started and just subtracting. That's the change in the position. And this makes sense because velocity is the rate of change of position. With respect to time. Velocity is the rate of change of position with respect to time. So integrating the velocity with respect to time from A to B gives the change in position from A to B. All right. Another thing that is useful, that's going to be useful, especially on the second quiz, is the relationship between the sign of derivatives and direction and concavity. So if we have a function that is, well, I'm just going to write it out. The relationship between sine, direction, and concavity. So there's a relationship. The derivatives tell us about, the first derivative tells us about direction, and the second derivative tells us about concavity. So here's how we can interpret some of these things. If we see that when a function is, when we see that the derivative is positive. So I'm going to say if f prime is positive, that tells us that f, the function, is increasing. And when the derivative is negative, that tells us that the function is decreasing. So first derivative, the sign of the first derivative tells us about the direction of the function. If we add to this, if we look at the sign of the second derivative, the second derivative is just the first derivative of the first derivative. So if the second derivative is positive, that means the first derivative is increasing. And if the second derivative is positive, that means for the function is concave up. And then opposite for negative second derivative. So the sign tells us about the direction or about the concavity, depending on which derivative we're looking at. So if the first derivative, the sign of the first derivative tells you about the direction of the function. The sign of the second derivative will tell you about the direction of the first derivative. The sign of the second derivative tells you about the concavity of the function. Also, since these things are all the same, the direction of the first derivative tells you about the concavity of the function. So if you're looking at a first derivative, its direction will tell you about the concavity of the function. Some of you have noticed that that is relevant to the second quiz. I've given you a graph and asked about the concavity of the function and to explain. You want to show that you want to explain using the direction of the first derivative because that's the graph that you're looking at.
And by greater than and less than 0, you mean above and below the x-axis?
Yes, positive and negative. So the other thing that we get, this is just reviewing what we know about derivatives and what they tell us about the graphs. To incorporate our fundamental theorem of calculus business into this, if the first derivative is positive, then the function is increasing, and the definite integral will tell you by how much, or the area, the area tells us by how much the function has changed. So for both of these, the area indicates how much. So if the derivative is positive, then the function is increasing, and the area tells us how much the function has increased or decreased. Any questions?
I have a question on the concave up and concave down.
Yes.
So does that mean that if the line is going down, it's concave down, or where it's underneath the x-axis? Because to me, this looks like if it's under the x-axis, then it's concave down.
If the second derivative is under the x-axis, then the function is concave down. Concavity is about how the function is bent. Let's look at our four different combinations of concavity and direction. Right. So let's look at combinations of concavity and direction. So we can have a function be increasing or decreasing. And a function can be concave up or concave down. So if a function is increasing, that means just the values are getting larger, or we're going up from left to right. If we want to, we can draw an increasing function that's concave up. Concave up means it's bent so that the spoon is going to spray water at you. The concave part is facing up. We can do the same, we can combine concave up with decreasing. We're going to draw a function that's decreasing, but we're still going to draw it concave up, so the spoon is still facing up. And of course, we put it in the sink directly under the spout. So we're not just washing the spoon, we're washing the counter as well. That's concave up. So if this is the graph of the function, we can see that the first derivative is positive because the function is increasing, and the second derivative is positive because the function is concave up. So I'm just drawing graphs of f. I can combine increasing and concave down, so I want to draw something increasing. But concave down means we put the spoon in the sink the correct way, and it's not going to splatter us with water. So here's concave down and increasing. It's going to be increasing and it's bent down. So the graph of the function will be increasing and concave down. We can draw a function that's decreasing and concave down. So I'm going to draw down from left to right. And the concave part will be facing down. All four of these segments are, they're not technically segments, all four of these bits of graph are the graphs of the function. So those four bits are the graph of f. In this first column here, we're seeing that f prime is positive because the function is increasing. So in this first column, f prime is positive. So if we look at the graph of the derivative, it will be above the x-axis. In this second column, the first derivative will be negative. So if we look at the graph of the derivative, it will be below the x-axis. If we look at this first row, where the function is concave up, that's where the second derivative will be positive. So if we look at the graph of the second derivative, it'll be above the x-axis. And when the function is concave down, the second derivative will be negative. So we look at the graph of the second derivative and it will be below the x-axis. When the second derivative is positive, we know that the first derivative is increasing. So if f double prime is positive, then f prime is increasing. And so that means if we look at the graph of f prime, it will be going up from left to right. And if the function is concave down, the second derivative is negative and the first derivative is decreasing. So here's the column where f is increasing, f is decreasing, f concave up, and then f concave down, the function. So positive and negative, we just look at above or below the x-axis. Increasing and decreasing is just the direction, going up or going down from left to right. And then concavity is how things are bent. Any questions?
Could you show an example? Doesn't have to, obviously not the test, but just,
So
I think
if we're
for me,
looking at,
I'm having a problem differentiating the concavity from the positive and negative stuff.
so we get the most information out of the derivative. So let me draw a graph, let's say x and y. Let's look at a graph of a function. And the function is just going to go, let's see. Up and then back down again. And let's just decide where these things are happening. Let's say this happens at 5, this happens at 10, this happens at 15, and this happens at, doesn't matter, 20. We'll call it 20 anyway. And let's say this graph that we're looking at is the graph of f prime. This is the graph of f prime. So this is similar to what you saw on the quiz. It's a bunch of line segments because it's easiest to see. So here we're looking at the graph of f prime. The sine of f prime tells us when the function is increasing. So we can see that the f prime is positive on the interval from 5 to 15. So f prime is positive on the interval from 5 to 15. So I'm using interval notation. Let's see. Get my red pen working. So on the interval from 5 to 15, f prime is positive, so we know that f is increasing on the interval from 5 to 15. Moreover, if I know that this maximum up here, let's say the top value up here is, let's see, that looks like it's about 12. And then down here, that's clearly negative 12. Because I can't resist symmetry. Moreover, we know that the function is increasing on the interval from 5 to 15. That area will tell us how much the function has changed from 5 to 15. So this area in here, I'm just going to call it A1. So that's just a triangle. So 1/2, I hid the 1. There we go. That's just triangle. So I'll just do 1/2 base times height. Base is 10, height is 12. So moreover, f has increased by 60 from 5 to 15.
Wouldn't it be 5, not 10? Because it's 5 from 5 to 10, the triangle, not 10?
Oh, I'm doing this whole thing, the whole section where the function is increasing. Area is the amount of increase. So f increased by 60 from x equals 5 to x equals 15. The area tells us how much has increase or decrease has happened. We also, if we look at where, since we're looking at the derivative, if we look at the derivative, the direction of the derivative, f prime is increasing from 0 to 10. So we would say the function f is concave up on the interval from 0 to 10. So f prime is increasing on the interval from 0 to 10. So f is concave up on the interval from 0 to 10. When we're looking at the derivative, the sign of the derivative above or below the x-axis tells us the direction of the function. The direction of the first derivative tells us the concavity of the function. Any questions? So we would also be able to say f prime is decreasing on the interval from 10 to 20. So the function is concave down on the interval from 10 to 20. So we can also observe that f prime is decreasing on the interval from 10 to 20. So f is concave down on the interval from 10 to 20. So the direction of the derivative tells us about the concavity of the function. The sign of the derivative above or below the x-axis tells us about the direction of the function. So if we look at the first derivative from 0 to 5, the first derivative is negative on the interval from 0 to 5. So f prime is negative on the interval from 0 to 5. I guess it is negative at 0, so I can include 0 there. So f is decreasing on the interval from 0 to 5. And the area would tell us how much. Since the area here, it looks like is going to be negative 30. So f decreases by 30 from 0 to 5. So if I call this A2, A2 is equal to 30. So f decreases by 30 from x equals 0 to x equals 5. Any questions? Then the last thing that we would want to observe here is how much the function is changing from 15 to 20. And we're going to make a similar statement that we did for the decreasing part from 0 to 5. We would observe that f prime is negative on the interval from 15 to 20. So f is decreasing on the interval from 15 to 20. The area itself is 30. The amount of change is negative 30. But if I said, what's the area of this triangle, we would say 30. If I said, what's the definite integral from 0 to 5, we would say negative 30. So f is also decreasing by 30 from 0 to 5. We wouldn't want to say decreases by negative 30 because that's a double negative. And in some languages, a double negative results in a positive, and in other languages, it does not. So a double negative should not be used for that reason. It's not a well-defined phenomenon. Any questions? Great. So if I wanted to draw this function, I would want to draw something that decreases from 0 to 5 and is concave up, and then increases from 5 to 10 while still being concave up, continues to increase from 10 to 15, but switches to concave down, then decreases from 15 to 20 and stays concave down. Moreover, it looks like we're going to finish at the same place that we started, because it decreases by 30, increases by 60, and then decreases by 30. So we'll end up back to where we start. So if we were to draw this, we're going to start and end at the same place. So whatever happens, wherever we start here at 0, I suppose I can just draw the y-axis here. So from 0 to 5, oops, there we go, there's the y-axis. So from 0 to 5, we're going to draw something decreasing. Oops, that's not the page. We're going to draw something decreasing and concave up. And it's going to decrease by 30. So here's our decrease of 30. So I'm going to draw decreasing and concave up. And that happens at 5. From 5 to 10, we're going to draw something increasing and concave up. And the amount of change from 5 to 10, the area is 30, so it just goes up another 30. And then we'll see an increase and concave down, because at 10, the concavity changes. But the amount of increase is going to be plus 30. So from the bottom to the top, that's a total of 60 of an increase. And then from 15 to 20, it'll get back to where we started. In this case, the graph should be two parabolas, and I drew it looking like two circles. So it should be two parabolas, but we got the big stuff. So if the graph flattened out, if the graph after 20 stayed constant at -12, there wouldn't be any concavity. So if the derivative is neither increasing nor decreasing, then the function will have no concavity. And that means that the function will be linear. So if the derivative is not changing, then the function has no concavity. That's a good question. No concavity if f prime is flat. And when I say flat, I mean neither increasing nor decreasing. Any questions? So that's the kind of thinking that you're going to need to do on quiz number 2. All right, so we're almost out of time, so we're going to put off looking at homework until tomorrow. So tomorrow, I want you to bring questions that you have, any remaining questions from chapter 5. We did a couple of questions from chapter 5, section 1. So let's look at homework questions from chapter 5, sections 2, 3, and 4. We'll bring those and we'll just try to go over as many of those as we can, get everybody caught up on homework, and then we'll move on to chapter 6. Any questions before we go? I need better glue to hold the laminate graphs together because I can't draw graphs with like a solid line. It almost just ends up fraying apart. All right, so bring homework questions from chapter 5 tomorrow. Get started on the 2 quizzes that you have this week. And that's it for today. I will see y'all on tomorrow.
Thank
Thanks
you.
for playing.
All right. Thank you, sir.